the synthesis of small molecules is very important in modern pharmaceutical industry. So we keep on developing new molecules that can bind to specific therapeutic targets to cure some important diseases. But as we're trying to tackle more and more challenging diseases, it's getting also more and more difficult to actually develop these new molecules. Right? If you think about the process of developing a new drug, it is both resource intensive and also takes a long time, right? So this shows how much time it takes, right, for different stages in a pharmaceutical discovery process, right, and how much money it costs. Right. So there are many important stages, but so what we are focusing on is this discovery phase, which we call hit to lead or lead optimization. This is where we identify sort of a pool of potential compounds, and we try to verify that they have the right activity or properties that we want, right? So in these stages, we need to synthesize and design hundreds to thousands of small molecules and be able to synthesize and test them in the lab, right? So being able to quickly design synthesis is one of the major bottlenecks for drug development, right? So traditionally, this has been mostly empirical, right? So chemists would, based on their intuition and chemical knowledge, to figure out synthetic pathways to target molecules. But recently, right, more and more people have turned their attention into what's called computer-aided synthesis planning. Right? So why is that? So first, in the discovery phase, we actually want to be able to actually make those molecules. So those molecules that can be easier to make would be prioritized in the pipeline when we try to develop new drugs, right? And for one target, there are probably multiple possible ways of making it. So it's desirable to also find more pathways so that we can select among them, like for improved reaction performances or like lower the cost. So people have more and more since then turned to computer-aided synthesis planning to use computer to identify possible pathways. And this could reduce personal bias because we're based on a computer algorithm, and it creates data in a more standard format so that we can more easily couple with automatic synthesis platforms. Okay. Also, we can better take advantage of the long history of chemistry and use all the chemical data as compared to any individual chemist who can probably have access to or be able to master a specific area of chemistry. Right. So to be able to do this, it's essential to have data sets. Right. Luckily, right, among the years, people have been accumulating data in chemistry and constructed some large chemical reaction databases. So some well-known examples is the USPTO dataset extracted by Daniel Long that has about 1 million reactions that is fully open source. And then there are some proprietary datasets. For example, the Reaccess dataset curated by Elsevier include more than 10 million reactions. Right, they are big data set. They have a lot of good information, but still there are some quality problems and missing information, which we'll talk about later. Okay. So with like these need for computer-aided synthesis planning and the data available for doing that, so all these started with a program called Make It, where we basically want to develop such a pipeline that can leverage computer assistance in finding possible pathways and do the synthesis planning by learning from data, and then take this computer-generated pathway and couple it with some automatic experimental systems to be able to actually make these compounds. So I'm going to talk about both these stages. So first, we're going to talk about how we can leverage computer power or machine learning in the synthesis planning stage. So that's that work is majorly, so mostly done by Connor Cooley, who was a longtime collaborator of mine, and he's now an assistant professor at MIT. And so let's start with what is synthesis planning. Right? So what we're trying to do. Right? So we need to first define this problem. And for synthesis planning, what we do is we have an input, which is the final target that we want to make. And we want to find these multi-step pathways that can decompose this target molecule to simpler and simpler building blocks, and finally to something that is easily commercially available. Right, so what we want to find out is the reactants, the intermediates in the steps, and also to carry out these reactions, we need additional reaction conditions like solvents and other reagents. Right. And so to be able to try to find these pathways, we need to digitally encode these chemical reaction rules, which we call reaction templates. Right? So this is a chemical reaction, and you can see, right? So not all the atoms in this molecules react, right? But there are certain atoms in these molecules that actually change during the reaction to form new bonds, right? So a reaction template is then trying to keep track of what actually changed during this reaction, as well as some level of molecular context around the reaction center, right? So we can go from a specific reaction to a more general reaction rule that specifies what actually changed in this reaction. Then with this general reaction rule, we can apply it to different molecules, right? So even if we're not dealing with exactly this molecule, we're dealing with a different molecule but has this substructure, we can apply the same temperature, the same template to break it down to possible precursors. Right? And so this reaction rule extraction process can be automated. So we start to do that on the available reaction records from the reactions database. So to extract about 2.5 million reaction templates from 12 million reactions, and then after some filtering based on the frequency of reaction templates, we get a data set of 16,000 most popular reaction templates, right, which we can use to then try to build the reaction pathways. So this is actually not something like a totally new idea. People have been thinking about this a lot, and traditionally this has more been a manual process. People try to encode these reaction rules by hand, and there has been some actually success stories, like the Chematica, which is now a company called Cynthia, right? So that does a lot of summary, right? So it now has more than 10,000 manually encoded templates to cover the organic chemistry space. Right? There are other works as well to encode these reaction rules. Right? So there's this reaction rule itself. Actually, they try to add some more chemical constraints about when can these templates be applied, or when are they restricted. Right? So these are the information that's typically added in these kind of manually curated templates. And so what we want to do for computer-aided synthesis planning is now we want to find possible rules to target molecule, right? And we not only want to find these rules and pathways, but we also want to chemically assess the viability or feasibility of these pathways. Among the feasible or possible pathways, we can then add further constraints to optimize the pathway selection to consider like other aspects like cost and economy. So this is a general workflow for synthesis design. So we start with the target compounds. Right? We can try to apply the reaction templates to these compounds to generate precursors. Right? And so we find a list of precursors, and then we can evaluate these reactions in the forward direction to see if it is chemically feasible. If it is, we check whether the reactants are viable. If they are, right, then if all the reactants are viable, then this search comes to an end and we successfully identified a pathway. Right? But if not, we will go back and if it is not viable, we will go back and further decompose these intermediate to try to identify viable compounds. But in the case, if we do not find any feasible reactions that can be applied to break down a molecule, or we have reached the maximum depth specified, we'll propagate failure. Right? So this branch is, we cannot search further. Right? So this is more like a live example, right? So you start with a molecule, you try to find some precursors, right? So some of the building blocks are viable, others are not. If they're not, you just keep growing this tree until you find something that's commercially available. And so this idea is straightforward. It's almost like playing any strategic game, right? You're just trying to use these rules to perform some kind of search to get to a target. But there are practically some challenges. So the first thing is kind of a common problem with all the searches is that right, if you go deeper in the search, the number of options can grow exponentially. Okay. Remember we said that we have a database of more than 160,000 reaction templates. Right? So for every molecule, probably we can find about 10 to 100 possible templates that can be applied to this molecule. And then if we are looking for synthetic pathways that are right, typical in chemistry, which can easily go up to tens of steps, right? The search space can be actually overly huge. So we want to be able to make the search process more focused towards those that are more likely to lead to the success. Right? So that means we need some way of prioritizing these options for each branch that we get. So we have explored different options, both on the precursor, like complexity of the precursor, and on the right, relevance of these reaction templates that are applied to the target molecule. So the first idea is simple, right? So essentially, we finally want to make the precursors as simple as possible. So we just want to, so we can just prioritize the precursors based on their complexity or how simple they are. Right. So this, so we can design some chemical scoring function to assess the complexity of a chemical. Right? This can be some simple heuristics that basically counts the number of atoms and bonds in a molecule. It can be some expert coded heuristics that incorporate a little bit more chemistry knowledge in it. Or it can be some predictive model based on some heuristic scoring, right, to get like predicted scores for chemical complexity. And it can also be some fragment-based definition, right? So if fragment exists in a molecule, it will be considered more difficult to build than others. Right, these are all approaches that have been previously explored. So these approaches work practically, but there are more complexity in synthesis planning that makes them not ideal. So in a multi-step chemical synthesis, you're not always right, building up structural complexity of the molecule. Right. For example, in chemistry, there's something that people encounter a lot is where you have maybe two spots that can react, but you want one specific spot to react. Right. So in this case, you do something called protection-deprotection. Right. So you use another chemical reaction to protect the other reaction sites, and then you react the site you want to react, and after that you deprotect, meaning that you remove those protecting groups. Right. So this is the example of a deprotection reaction. Right. So you are removing some protection group to get to the final product. Right. So then this step is synthetically considered making progress. Right. So you are getting closer to your target molecule. But in terms of molecular or structural complexity, it can be decreasing, right? So you're essentially removing some structure from this molecule, right? So if you use a fragment-based scoring for your molecule, right, this molecule will be considered more complex than this molecule, right? So in this case, right, you actually have a decrease in the molecular complexity score, whereas you are actually making progress in terms of synthesis. So there's this contradiction here. So Connor developed this, turned to this like learned heuristics approach, right? So then what he does is he tried to use reactions to separate or to define the complexity score of chemicals. The assumption is that, right, so we have all these reactions, and we assume that they are synthetically all constructive, right? Meaning that we're doing meaningful synthesis. So the complexity score of the product should be higher than the reactants, right? So then we can train a machine learning model, a ranking model, right, that tries to separate the reactants and product, right, making sure the product receives higher scoring than the reactants, right? So by training a model like this, you can separate all the chemicals based on, right, the reactions between them to get a more synthetically meaningful complexity score. Here's an example, right, showing that for a drug molecular target, and these are the synthetic steps. If you use like simple heuristics approach, you see that, right, basically they don't really agree with the what's actually done in the synthesis. They think the molecular complexity is decreasing from the reactant to the product, but the learned heuristics more correctly recognize that through these synthetic steps, we're actually building up complexity in the molecules. So that's how we prioritize different molecules. And for the reaction templates, we also have a way of trying to prioritize them. Right, so this problem is formulated as a problem to select the most suitable policy or action policy reaction template to break down the target molecule. So we use all the reaction data records and treat them as pairs of target compound and reaction template. We try to learn this relevance between the target molecule and reaction template. And so we treat it as a classification problem. The output would be like a one hot vector of a length of 160,000. So by training this network, we can learn which reaction rule is mostly applicable to this target molecule, right? So then we can focus on more the reaction templates that are more likely to lead to meaningful transformations. Okay, so that's basically what we do with the retrosynthetic search framework. Right? So we have a basic search framework, and then we use some heuristics both with chemicals and with reactions to help make the search more focused and well prioritized. And during this building up this framework, we also need to make sure that the reactions that we found are chemically meaningful. So we have some additional steps. So one is to predict the reaction conditions for the transformations that we found, and then we need to evaluate whether we can actually get the reaction outcome that we want. Right. For the reaction conditions, we actually want to, right, so we know what transformations that we want, but we need to propose what kind of solvents, catalysts that we need or we can use for these reactions. And so in this case, we looked at solvents, catalysts, and reagents, as well as some continuous variables like temperature that can affect the outcomes of this reaction. Right. Again, we turned to the database of reaction, a large database of chemical reactions, and we formulate this problem as a classification problem because all these catalysts, solvents, and reagents are commonly used. Right? So in the end, we do not have that many types. Right? We have 800 catalysts, 2,000 reagents, and 200 solvents, which has many reaction precedences in the data set. So we can try to learn, right, how those reactions map to these different type of catalysts, reagents, and solvents. Right. So what we want to do is we train a neural network model that does this job. Right? So given this reaction transformation, we'll have the model to predict the catalyst, the solvents. Right? There can be multiple solvents, multiple reagents used for a reaction. And finally, temperature. For reaction condition, usually there are multiple sets of conditions that might work. So we looked at like top 10 accuracy, which is about 60%, which is reasonable for this task, just, so that we can get a kind of reasonable guess of the reaction conditions for these reactions. And even if the model is not predicting the exact correct reaction, it's usually predicting a similar set of compounds that when we evaluate them by the eye, they seem reasonable. We also found that through this process, while we treated these reaction conditions as just discrete labels, through the learning process, the model is able to learn the similarity of these chemicals based on how they are used in the reactions. Right, so we can go back to the weights of the trained model and extract some vectors that can be used to represent similarity. And we did some visualization to condense them into a lower dimensional space using the t-SNE approach. And then we manually label these conditions, like the reagents and solvents. And we found that, right, the clustering results from the latent embeddings actually matches very well with the human labeling of these different types of chemicals. And then the next step is we want to evaluate whether or not the reaction can actually get the outcome that we want. So then this problem becomes, if we know what we start with as a reaction mixture, what can we get as the major product? Right? So the main problem we have in trying to predict the outcome of a chemical reaction is that we really don't have negative data, right? So in the database that we have, so it's highly biased towards reactions that actually succeeded. And not a lot of reaction that people report actually have zero yield, right? Meaning they're failed reactions. But so there are actually a lot of failed examples, but just the practice of this area is that people tend not to record or publish it. Right. So we need to do some data augmentation to create some negative reaction data so that we can either do a classification or ranking to try to predict the right reaction outcome. Right? So this earlier approach by Connor took this template-based approach. Right? So we have all these possible reaction templates, and so we can apply them to these reactants that we have that can help us generate a pool of possible candidate products, and then we can, which might or might not include the recorded product. Then we can put them all together and train a machine learning model to predict, right, to rank these recorded product higher than all other possible products, right? And so then this is a two-stage approach, right? The first stage does some forward enumeration to get all the possible candidates, and the second stage is a ranking model that tries to rank the recorded product better than all the other candidate products that's generated, right? So I'm gonna skip the formulation of the model details, but it's just trying to treat the chemical reaction as a bunch of graph edits and use that to get the final score to help rank the possible candidates. So this was kind of one of the first works that does this reaction evaluation task on a large scale. And so it demonstrates strong promise, right? But the accuracy is not like super high. Right? We have the accuracy about 30%, and so there's room for improvement. And this template-based approach also limits the kind of negative data that you can generate. And also, this template application is computationally expensive because it has to be done in a CPU. Right? So later, this approach was further developed into a template-free one. Right? So when now we can treat the molecules as graphs, and so we can first identify the reaction center, and then treat the reactions as graph edits to these molecular graphs. Right? So then we can generate some random permutations or random graph edits that leads to a set of possible outcomes, and again, try to predict which candidates is the most likely. Right? So it's again a two-step. We first predict the reaction center and then rank the possible candidates, but it now gets rid of the template application, and these graph edits enumeration can be performed on GPUs, which make this process much faster. And also the elimination of templates made this approach able to cover a wider range of chemical reactions, and it got more accurate. So with this graph-based approach, we can also take advantage of some like the attention mechanism, right, to generate some interpretation into the model predictions. So with the attention scores, we can actually look at when the model is making predictions, what part of the molecule is it looking, right, making the most attention to. So that can tell us, right, how the model is actually making the predictions. There are some examples where we do see right? The model highlights the parts, the atoms with the highest attention score, especially when there are multiple sites that can react, right? We know that, right? So the model is looking at some sites over others to find the reaction site that probably has the highest reactivity. Right? We did some more examples, right, that show that the model is able to learn from a lot of data to find the right place to look at in a molecule to make the right predictions. We also did a kind of a human benchmarking to see how the model is performing compared to human experts. So we picked some examples, like about 80 reactions with different popularity. Right, so we can see, right, the less popular the reaction templates are, the lower accuracy that the model has. And so this is what the model does. And then we compare that with some human performance. Right, so these are 10 chemists, chemical engineers with different level of knowledge. And we see that the model performance kind of lies in the upper range of the almost among one of the best, right, comparable to one of the best human experts. Right. So this sort of are the essential elements of this synthesis planning framework. Right. So we first establish a library of reaction templates that can be used to search for potential pathways for a given chemical. Built this retrosynthetic framework. Then we designed some heuristics to make this search more focused and effective. And then for every reactions that we found, we can propose reaction conditions and evaluate whether or not we can actually get the desired outcome that we want for this reaction. So there are some other details, right? So eventually we want to stop, right? So how do we define whether a chemical is commercially available? Of course, you can use a catalog of chemicals that actually are sold commercially, or you can use other kind of criteria or heuristics, like how many times have people used this chemical in the data set. Right? It's called chemical popularity, and you can also use those kind of structural complexity scores. You define, right? So if now we have a model that has a structural complexity less than a certain threshold, then we stop the search. We consider it simple enough that we can stop. Right? So all these kind of elements come together to form this platform for computer-aided synthesis planning. Of course, we later added in some user customization approaches, but based on how practitioners actually want to use this tool. So maybe there's a desire to blacklist some chemicals, might be toxic, and people don't want to use. And the ability to save and revisit previous results and refine them. Right. So this has been developed into a tool called ASCOS, which has many users around the world. And then this framework was used in some real case studies, right? So for some new drugs, which has not been made before. This was back in 2018, 2019. But at that time, right, this is a newly approved drug. And so we used this platform to try to identify synthetic routes for it. And we were able to find a 13-step synthesis within 1 minute time that decomposed this initial, the complex molecule into some simple building blocks that are cheap and viable. Okay, so that's the synthesis planning part, right? So next, I'm going to briefly talk about the robotic execution part. So this part I'm less an expert of, but it's kind of fun to see how the synthesis is actually carried out, right? So this part, right, so was led by, again, Connor and experimentalists, chemists, and a mechanical engineer, Justin and Dale, to actually construct this robotic system and take in programmed instructions to carry out the synthesis. Unfortunately, right, we still need some expert input to further refine the computer-generated synthesis plan that we just discussed. And so one of the main reasons is that, so most of the syntheses are carried out in batch mode, but we want to do this synthesis in a continuous fashion, right? So the recipe has to be somehow modified to make it more compatible in flow. Right? For example, we want to, we probably, in flow, we need to have the reagents soluble in the solvent, whereas in batch, it's okay, just stir the system, right? So we still need some expert input, but the computer-aided synthesis planning at least gives us a very good initial idea to come up with the recipe that we can finally use in the automated synthesis. Right, so this is the system, right? On the left was the synthesis planning framework that we just talked about, right? We start from a target compounds and come up with a synthetic routes that seem to have high likelihood of success. And then with some expert inputs, we can program them into a synthetic procedure that can be then taken by this robot to assemble the reaction system and run the synthesis. Right? See, the system actually consists of a robotic arm that moves and assembles the reaction modules onto this process stack. And then there on the left, there's modules for reagent storage and pumps to feed them into the reactor to start the reactions. Right, so the hardware system, right, it consists of process stacks with characterization rules to measure temperature and concentration and stuff, right? And then different reaction modules for different kind of reactions. And if there are multiple steps reactions that probably need purification, there's separator modules. And the robotic arm will assemble these in a sequential manner so that it can run the reaction. And then after each reaction, it will automatically reconfigure the system for the next reaction to run. Okay, so this is kind of an animation of, or a video, sorry. It's a video of how the system works. So you can see this is actually 30 times speed, right? So it's made much faster. The actual movement is much more slower than this. But you can see how the robotic arm is working to assemble the necessary reactor modules to make this system and make this tube connections to have the right material flow, and it can close the reaction system and start the feed to carry out these kind of multi-step synthesis. After the synthesis, it will first disassemble the reaction system and then reconfigure it for the next reaction. Okay, so we use this platform to validate it in actually a number of real syntheses. covering many different scenarios, like back-to-back synthesis of two different compounds, parallel synthesis of two compounds that share some reactants. We tried some more challenging synthesis that have specified stereochemistry. And we also tried what's called library synthesis, where we're trying to make a library of compounds that have some similar structural features. So that's pretty much what I want to introduce today. So, so this field is continuously under development, and so there are still some challenges outstanding that we need to solve. The first is about the availability and quality of data. So the more data we have, the more powerful that we can make the models to be. And so again, for multi-step synthesis planning, there's not really a clear evaluation criteria, right? So about which paths are better than the others. So as we accumulate more experience and success in these areas, we need to probably have a better idea of how to define what is a better multi-step retrosynthetic pathway. Model interpretability is another thing. So if we want to work with chemists, we need to not only provide predictions, but need to know the underlying reason for the model to make these predictions, so that chemists can actually accept these black box predictions, especially when it does not agree with their knowledge and intuition. Okay, so many of these slides are made by Klaus and Connor, and so these are other collaborators in this project, including a few computer scientists, chemical engineers, and experimental chemists. Okay, that's all I wanted to say. Thank you very much for your attention, and I'd be happy to take questions you might have. Okay, if no questions.
Thank you very much.